John Kinney, and thank you for joining our session today titled Dynamic Spectrum Sharing, Driving 5G to Scale. Before we get started, a few housekeeping items I'd like to go over. We are recording the session today, and we will make a video of that recording available to our participants on our YouTube channel. The slides from the presentation will also be available to registered attendees after we're done. And we've got an in-depth companion report on this topic that will also be distributed following the session. Finally, I'd encourage you to use the webinar portal to submit questions throughout the presentations. We've set aside some time to answer those questions, and we'll get to as many as possible following the presentations. So with that, it's my pleasure to introduce our panel today. From Ericsson, we've got Sibel Tombaz, who's head of 5G high band and active antennas product area networks. And from Rohde and Schwarz, we're joined by technology manager Andreas Roessler. Thank you both very much for sharing your perspectives today. Now, I'd like to provide a little bit of background and context before turning it over to our experts. First, what is dynamic spectrum sharing? This is a technology that allows operators to simultaneously transmit LTE and 5G NR signals in the same band at the same time. Base station scheduling software dynamically allocates resources based on network usage patterns and what they're seeing in terms of UEs. There's two kind of ways to do this, and this is going to be incredibly topical explanation. Our experts are going to give you more information on this. But first, the problem that DSS is solving for is collision of LTE and 5G synchronization signal blocks. So the multicast broadcast signal frequency network approach blocks the LTE pilot signal and inserts 5G NR synchronization signal. The non-MBSFN method puts shortened 5G NR synchronization symbols in place of the LTE equivalent. So that's a very kind of general description of how DSS works. So what does that mean for operators? Well, in short, it means a lot. You've heard the term 5G ready used in the context of LTE investments. So a lot of the RAN infrastructure deployed over the last few years can support dynamic spectrum sharing through a software upgrade. So instead of physically sending crews out to these radio sites to redeploy spectrum for 5G, it can be done remotely. So that has huge implications for not just OpEx, but also for the time it takes to deliver service. The other big piece here is the transition from non-standalone to standalone 5G networks. When you use DSS as a bridge, if you will, to put in a coverage layer, you're transition to the 5G core and you're there for the most part. So that's very important when you think about the enterprise-facing services that so much 5G hope is pinned on. The faster you can get to standalone, the faster you can get to new service revenues. To give you an overview on how operators are approaching DSS, I thought I'd give a bit of a broad look and then focus in on two particular carriers. First thing to note here, Ericsson spectrum sharing is the only commercially available DSS solution right now. So according to Ericsson, more than 80% of their customers testing the Ericsson spectrum sharing solution plan to deploy it in the coming 12 months. In the US, AT&T and Verizon are obviously both Ericsson customers, and they've both articulated plans to use DSS as soon as the latter part of this year. More globally, we've seen public statements regarding DSS strategy and testing from executives with Ooredoo and Qatar, with Play, Swisscom, more on Swisscom in a moment, and with Telstra in Australia. I'll talk a little bit about how Verizon is planning to use dynamic spectrum sharing. I looked back through my notes, and the earliest reference I found came from their CEO, Hans Vestberg, during a quarterly call in August last year. He said DSS would effectively let Verizon have 5G capacity and coverage using the spectrum assets they have. And obviously, we've got some machinations in the US going on around mid-band that would color that strategy over time. But for now, DSS, very good path forward for Verizon. As they deploy 5G today, that's largely focused on millimeter wave in the densest part some markets and also in NFL stadiums and arenas used for professional basketball and hockey. I think the idea here is to provide that differentiated experience of 1 gigabit per second plus speeds as opposed to low band 5G where the performance isn't remarkably different from LTE. Then in Q4 last year, Verizon successfully tested DSS using Ericsson and Qualcomm equipment. And in terms of when they plan to deploy the technology, a spokesperson told us last week that the decision will be based on customer experience. And she made clear that all 3 of their RAN vendors don't have to have a DSS product before the feature can be rolled out, which is a interesting tidbit given the lack of support across vendors, which we'll talk a little bit more about in just a minute. To talk a little bit about what Swisscom is doing, they have an end-to-end deal with Ericsson, and they were an early mover in commercializing 5G using their 3.6 gigahertz spectrum. They claimed nationwide coverage in November last year, I believe, and that equates to 90% population coverage. And although public sentiment in Switzerland has slowed 5G deployments at the moment, Swisscom plans to use DSS, and they've successfully tested the technology on their own network and in a transmission between the Swisscom network and Telstra in Australia. In terms of public criticism of DSS, the statement on your screen is from T-Mobile's Neville Ray. This is really the closest we've got in terms of public commentary in this regard. To break this down, he says there are vendor delays. We talked a little bit about that earlier, and if you recall the Verizon slide, we established that not all vendors needed to support DSS in order for an operator to use it. He also comments on the net capacity loss observed when DSS is used. You'll hear more about that from our panelists today, but to put a finer point on that, some analysis published this morning from Frank Ryle projects a net capacity loss of between 10 and 20%. And it's also worth noting that a combined T-Mobile and Sprint would have millimeter wave, mid-band, and low-band spectrum resources, so they won't necessarily need to use DSS. I think that adds some necessary context in terms of these comments and how they fit into a competitive landscape in the US. So with that, I'd like to turn it over to Sibel to advance the presentation and share Ericsson's perspective on dynamic spectrum sharing and what it's going to mean going forward for 5G. So Sibel.
Thank you, Sean. I will share my screen now. So good morning, good afternoon, and good evening, everyone. Thank you for joining this webinar on dynamic spectrum sharing, which we call Ericsson spectrum sharing. So my name is Sibel Tombaz. I am heading up 5G high band and active antenna systems group in Ericsson, and I'm also responsible person of Ericsson spectrum sharing product. And today I would like to talk about dynamic spectrum sharing as a technology, the importance of realizing 5G vision, which requires high spectral efficiency, nationwide coverage, low latency, and indeed SA architecture. And then later we will zoom into the solution itself and explain how it works and try to cover some of the questions that has been mostly asked regarding the capacity loss and performance impact in the network. And I will also talk about the global readiness and the ecosystem around Ericsson spectrum sharing. So before we start our presentation, I would like to share some good news with you in case you haven't seen. Our Ericsson spectrum sharing solution has been awarded 2 prestigious awards from GLOMO. And one of them is the Best Technology Breakthrough Award. Another one is a CTO award, which is quite prestigious because it's been selected by more than 20 CTOs of leading operators as the key breakthrough of last year. We're of course very happy to get these awards, which we have been working for some time, and I'm very happy that I had a chance to talk to you about this important breakthrough for wireless communication. So before I start talking about dynamic spectrum sharing, I would like to spend a bit more time to explain why we need low band in general. And when I mean low band, I mean for all FDD bands. In my vocabulary, 1800 and 600 are defined as low bands. When we look at for the 5G vision, As we all know, this is a technology where it has been designed not only for mobile broadband, but also for different use cases. And we would like to understand what exactly that means and what this kind of network requires to be able to support these different use cases. In Ericsson, we divide these different areas into 4 different categories. We have, of course, enhanced mobile broadband, that is consumer focus, the use case that we are used to from 4G. Fixed wireless access has started with 4G, but we believe there is a quite big potential for 5G. And of course, there is massive IoT and critical IoT, where there are different requirements from the network in terms of coverage, latency, and reliability. And as I mentioned, all these different networks and deployments require different KPIs for network to provide. But if I look at in general, there are really key building blocks for 5G to provide in order to serve these use cases. The first one is, of course, capacity and peak speeds. In order to handle billions of devices and a huge amount of data traffic, we need a 5G network that can support high capacity and high peak rates. And for this case, we definitely need new bands. We need mid bands, we need high bands that can provide this quite big amount of peak rates and capacity. But it's not, of course, sufficient. We need low latency, and we need network slicing. This is the only way where we can define and satisfy different quality of service requirements for different use cases, because we now need to handle for different expectations for different devices. And for that, we need standalone architecture. This is definitely key for any 5G network to use for architecture to be able to have both latency and the slicing benefits. But of course, a network that needs to provide these use cases that requires mobility, you need to have coverage. And the coverage is always the king, and it will be the same for 5G. And here where it comes the importance of low bands. But it's also important to understand, and all these key building blocks, new bands, standalone, and low bands, are extremely dependent to each other. And especially standalone 5G, we believe that cannot be done before we provide network-wide coverage. And I will explain why that is with a bit more details later. So overall, Ericsson's position is that in order to realize 5G vision with supporting one network for multiple use cases and industries, we need to combine the benefits from all different bands. We need mid-band to be able to add capacity. We need high band for extreme capacity and extreme latency and extreme peak rates. And we need low band as a complementary and supporting band for both these TDD bands that require higher efficiency. And here, it's really key to be able to compensate these 3 bands together to be able to support this full vision 5G network. So let's zoom into low band a bit more to explain why we say that is essential for 5G networks. So of course, and this is also one thing that 5G low band provides more than nationwide coverage. And here we try to provide 4 different reasons. Of course, a race for nationwide 5G coverage is essential part that is motivating low band. This is definitely one of the initial motivation for operators to go for NR on low bands. But when you actually look at it, it always took much longer time for any generation to provide nationwide coverage. And that was due to the fact that all new generation required a new band, new hardware, and visiting every single site, which of course, not only is very costly, but is also very time consuming. And this was generally delaying this introduction of this new technology in the rural and suburban areas. With 5G, it will be different because low band is one of the bands that you can run 5G on. And with our software and the hardware 5G capable radios, it will be only software upgrade to be able to support this nationwide coverage. And it's definitely key, important for operators. Another reason is spectral efficiency. As every generation, spectral efficiency of 5G is higher compared to LTE. And that has different reasons in terms of spectrum utilization. It has much lean design, and it also provides lower latency inherently compared to LTE, which means that operators, regardless as the new penetration increase on 5G, will be motivated to migrate their spectrum to 5G to increase the spectral efficiency of their band, and there's very, very valuable FDD bands. Another extremely important aspects for motivating in our low band is boosting the coverage of mid band and high bands. Here we give an example for mid band. but it's the same thing valid for the high bands. So as we know, in the TDD bands, they are all limited by uplink. It's because of the TDD nature, and it's also because they are higher bands. And we see that when we do correlation between FDD and TDD bands, there's a significant increase in terms of coverage that are maximizing the spectral efficiency of this NIF spectrum as well. And the final reason for low band is standalone. And here I will zoom into a bit more later. We all know that standalone is definitely key for this 5G vision. As I explained, is the fact that we have lower latency, we have network slicing, and the fact that we can also access the larger spectrum instantly instead of higher latency that comes from NSA networks. But as we know in this architecture, first of all, we will need to write voice, and voice generally likes FDD bands because it requires coverage. That is definitely another reason why we need FDD bands for all the 5G networks. Another reason is that SA networks, there will be call to service requirements. So if we cannot guarantee a coverage, the UE will be moving between LTE, EPC, and 5G core, and this will definitely degrade the user performance. And operators cannot really satisfy the call to service requirements of these different use cases. And therefore, we always need an NR layer where the devices can fall back to, and they don't need to rely on LTE and EPC. So I would also like to share some interesting results, the potential study that we had done by our Ericsson Consumer Lab. And here we have asked consumers in different countries whether they will switch to operator if their own operator doesn't switch to 5G and someone else in the same market does. The results are definitely very interesting. And if we just zoom into United States, and we see that 1 in 4 consumers said that they will switch the mobile provider within 6 months if their own operator doesn't have an offer for 5G. And 1 in 10 said that they will change immediately the operator because they don't offer 5G. So this also shows another important aspect for operators' business, why they need to race for the 5G and why they need to access for higher coverage and potential use cases for 5G. And this is, I think that's definitely another reason why we see a quite high interest on low band, which is the easiest and the most cost-efficient ways of introducing 5G in their networks. And I would like to now spend a bit more time on looking into an example network, how the migration to standalone will happen, and why Ericsson spectrum sharing is key to enable the migration to SA. Let's take one operator that have a good LTE network that is indicated as this green FDD layer. And they also acquire a new mid-band spectrum. Let's assume 2.6 or 3.5 gigahertz TDD bands. And initially, they will just deploy this new band with the new hardware in an existing site. But as we all know, TDD bands have issues in terms of coverage. And we see the same things for high band, and it's valid for the mid band as well. So when we compare the coverage area of mid band compared to FDD bands, there's of course a significant difference what 1800 FDD can access versus the mid band. In order to kind of solve this problem, we have another unique solution called uplink booster, which extends the mid-band coverage significantly and increases the population coverage by using this NIF spectrum to 45%. However, there's a quite big gap between what 5G can provide versus the existing LTE network can provide. And as we all know, initial deployments has been focusing on NSA, which is actually quite good architecture in terms of coverage, and if it is for mobile broadband. So in NSA, as we know, we have LTE and RDOA connectivity, which means that there is a benefit by utilizing LTE to increase the coverage because the user can actually switch the uplink whenever it has an issue with coverage. And this gives quite significant coverage gain to these deployments. And here in this example, the population coverage is increased to 67% utilizing NSA. So this is now the baseline. This is an operator now has been deployed. NSA has acquired a new spectrum like midband, and it's quite a good launch. But now they want to move to SA because that is the final architecture, and this is the only way they can look into different businesses and different use cases. So what will happen is that if they go to SA without investing and looking into their coverage layer, they will lose coverage, because you suddenly lose the NSA and the link between your mid-band and your LTE band, which means that you actually move to standalone because you really wanted to go for call to service, you want to do for different use cases, and yet you actually start creating a shorter, a smaller areas where there is a 5G coverage, and then there will be a quite significant part of the user, the area where the user still needs to fall back to 4G. And that is the place where the low band is becoming essential. So if suddenly we can turn one of these LTE bands to NR using spectrum sharing, so with this case, then I will provide a full coverage of 5G in the network, which in this case, then at least the device will always be connected to 5G core with different call to service, of course, but then at least operator can connect them to 5G and 5G core and get benefit from different benefits of 5G instead of falling back to LTE. But this is not the only reason. I can also do carrier aggregation between now these two different bands. By using mid-band and low-band carrier aggregation, I can now increase the cell coverage significantly. By doing that, I now increase the coverage of mid-band to 84% compared to what FDD can provide. Which means that providing and enabling NR on FDD bands using spectrum sharing is not only provides nationwide coverage because of FDD, but it actually increases spectral efficiency of your TDD band, which is essential. And this is the case where we believe the only way operators can actually switch on standalone and look for different use cases, because now their network is prepared in terms of coverage, capacity, latency, and peak rate. Okay, so far we have been looking into why low band is essential for 5G networks and what kind of benefits it provides. But of course, there are different ways to enable 5G on FDD bands. And here we summarize 3 cases. Of course, one option is to switch off one of the LTE carriers and then start running 5G in that band. And of course, this is quite a significant impact because LTE load is still high. And in that case, there will be a quite big hit on the LTE capacity and user throughput in the existing devices. The second option is static sharing. It actually means that you take one of the bands and you just statically divide it between 4G and 5G. So in this example, there will be a still significant impact on the LTE side because as users suddenly only access half of the spectrum, and also the load of that carrier will be significantly higher, leading to lower performance. And also for 5G part, this will also limit what the peak rate and user throughput that you can get from that spectrum. And I think that is the key benefit of Ericsson spectrum sharing. The fact that you can actually run 4G and 5G in the same spectrum, and you can dynamically allocate the PRBs based on the traffic load, user demand, and experience requirements. You can actually don't need to provide any static refarming and just let the network to define how to divide the spectrum between them every millisecond. And this is, I think, where the key benefits for operators comes. That all this very long and kind of long waiting for refarming and planning is now done by the network in a millisecond level. And let's zoom into the performance. This is an area definitely is highly asked. What is the impact of doing spectrum sharing? And here it's really hard to look because it's really important. What is your baseline? If your baseline is that you have a certain LTE band and you suddenly do spectrum sharing, and what will be the loss of that LTE band? That is one of the comparison. But of course, the comparison we should really make is what will I do compared to static spectrum sharing? Because I think if you might really make an apple-to-apple comparison, you need to compare 2 solutions where it provides both 4G and 5G coverage in the same network. But here in this bar, we are trying to summarize all these 3 options where you can see the relative difference between different solutions. So if we start from the first part, where there's a comparison at the low load. And here at the baseline, we have 20 megahertz LTE carrier. And the user throughput has, let's say that assume that we have some user throughput that come from that LTE band as a baseline. Of course, if we do static spectrum sharing and divide the band to 10 megahertz to LTE and 10 megahertz to NR, then the user throughput from for LTE and 4G and 5G users will be halved compared to what they had before. And if I instead do dynamic spectrum sharing, which not only gives me the pooling benefit, but also optimization choice, because I don't need to statically refarm, it actually gives a significant benefit compared to static spectrum sharing. So in this example, at the low load, we have 86% improvement for the LTE user throughput and 57% improvement for the NR user throughput. But this is only for the low load. I think what is really essential to see the benefit is actually at the high load, which is basically most of the cells today. And when we look at the 2020 scenario, and here you will see why most of the operators will start deploying ESS this year. Because in the beginning, we will have very, very few NR user penetration. And having a static sharing and putting a certain bandwidth and taking away from highly loaded LTE band will not only take away certain bandwidth from LTE user, but essentially what will actually do is it will increase the load and increase the interference in the LTE network, which will actually reduce the user throughput by more than 70% compared to what it was before. So in this example, doing spectrum sharing, it has almost increased the user throughput by 3 times compared to static spectrum sharing. And for me, this is the real value of pooling, real value for network optimization when you have the full access of the whole spectrum and you can decide based on millisecond level information instead of static sharing. Another important observation that we see is that spectrum sharing is not only when there is an imbalance between number of users between 4G and 5G. It's actually as important when we have the same amount of devices supporting 4G and 5G. And here we can refer to 2025 figure on the bottom. And as you can see here, the pooling benefit of spectrum sharing will always be there. And therefore, we believe that spectrum sharing will be a long-living solution, which can be even foundation of 6G going forward. Because the pooling benefit of spectrum, the fact that you can optimize the efficiency will be that regardless of the imbalance between the devices supporting different technologies. So overall, yes, spectrum sharing, when compared to baseline, has a small impact on the user throughput. But the real value and real comparison should be between static sharing and dynamic sharing, where we see up to 3 times user throughput gain for the existing devices when we do the sharing through dynamic way. Okay, so I will try to explain how the solution works. If we just zoom into spectrum, and if we just look into how the PRBs and will be allocated in the frequency and time domain. This is definitely a quite complex solution. And I think that has been the reason maybe we have waited so long to have such a solution that can divide the spectrum dynamically between different technologies. So what actually happens is that here, based on the information about the devices and their demands and the load levels and amount of data in the buffer, the network, which is the brain of the solution, is actually decides how much spectrum should be given to 4G and 5G users in every TTI, in every millisecond. In some cases, we can see 2 devices in the same TTI, and then we decide certain division. And in the next TTI, we might see that there is no 4G device, and we give all the spectrum to 5G, and vice versa. And this will be based on instantaneous information and directly handled by the device, directly handled by the network. And one important aspect to highlight here about the device. So this is completely transparent to the 4G UE. Actually, 4G device doesn't even realize that there is a 5G is sharing the same spectrum. However, 5G user actually knows. They know that they are using the same spectrum together with 4G. And that has been done by the communication together with the 4G. And this has been secured in 3GPP, the fact that informing the 5G device that the spectrum is now shared. And they need to be respectful to the reference signals that are transmitted from LTE, even when there is no data transmission. And on the other hand, in terms of dynamically sharing, there is no impact by the device. So all these are completely handled by the network, and the device only sends the data in the uplink and receives the information based on the information from the network. And network handles all the dynamicity in the given TTI based on the information that they receive by the UE. Okay, and of course it has been a long journey to reach here. The initial part of the solution, I mean, when we started, it was around 2017 when we started first working on the concept, and we believe the success of the solution is mainly come from the fact that we start working with our chipset partners from the beginning. And this, of course, allow us to drive the solution together with the ecosystem into 3GPP, providing all required messaging requirement between network and device. And according to them, we can focus on our implementation and the dynamicity optimization accordingly. And therefore, we are very happy today, after 2 weeks ago's announcement for the GA, that we actually, after a long journey, we bring the idea to a commercial solution as of 2 weeks ago. So I would like to have this chance also to spend a bit more time on zooming into Ericsson spectrum sharing and why we say this is a unique solution and what are the additional benefits that we provide to our customers. First of all, our solution is cost optimized. So our customers can actually share all the hardware they can have instead of radio, baseband, and the SIP relay. So all the hardware they have been using for 4G that are 5G capable, they can just be exactly used for 5G. And that, of course, brings the fact that it's more sustainable, because then we don't need to bring any new hardware to the site and just do the upgrade over the air, and we can just run the spectrum sharing nationwide in this network. The performance value really comes from the fact that we can do the sharing in millisecond level, and which is really key. Here, as you know, the TTI is 1 millisecond in LTE, and to be able to adapt to the millisecond level changes in the traffic gives a significant performance gain for Ericsson spectrum sharing. And finally, remote software installation and the time to market for our customers is definitely the key. And the fact that all ecosystem support for all the chipset vendors and our engagement with them is also enable the global launches that are prepared the ecosystem. So just to highlight or at least say a few words about why we say millisecond level sharing is key. And here I would like to just share some numbers. In the left side, you're actually seeing some PRB utilization from real traffic. This is one of the networks that when we look at the TTI utilization for different cells and also zooming into the certain minutes, then we can see how it changes between different days, between different cells, and also when we zoom into the 5 minutes, how it changes. So it's definitely essential to understand that there's a big change between traffic between one cell to another, and there's one TTI to another. You can actually see one TTI is 100% utilized, and you can see 10% utilization in the next TTI. And this definitely indicates that if you are fast and can adapt to the traffic level fast, you actually increase the spectral efficiency. And here we do the simulations to adapt and understand how much gain we are talking about, and you can see the figure on the bottom here. And if you do the spectrum sharing in every 100 milliseconds or 10 milliseconds, which means that you need to pre-allocate spectrum to certain technology in advance, because you don't know what will happen 100 milliseconds later. And this comes with inefficiency. And here you can see that by doing spectrum sharing in every millisecond level, you can increase the user throughput of a cell edge user by 2 times. And average user throughput can be increased by 25%. And in terms of capacity gain, we actually get more than 20% capacity gain in the same spectrum, which means that spectrum sharing is essential, but doing it in the right way, it's actually had the potential to increase the efficiency even further. So few words on the ecosystem. And I think, as you mentioned, there are quite good references that been highlighted by different chipset vendors and also OEM vendors. I mean, we have been working for most of them from the beginning, and we have secured interoperability testing with all the major chipset vendors. And we have been also testing some of the initial devices. And we are very happy to see that this year, 2020, will definitely be the year of the spectrum sharing. We will see all the commercial devices, we will see all the commercial networks, and we will see that all these 5 million radios that are ready for 5G will be switched on. and will be running this software during 2020. So to conclude my presentation, I would like to highlight a few things. So first of all, definitely spectrum sharing is important for realizing the 5G vision. This is not only about nationwide coverage, but it is key to migrate to 5G standalone and boost the coverage and capacity. It's a better way to build 5G because where you share all the hardware you can have and to increase the value of overall network spectral efficiency. And doing spectrum sharing is one thing, how to do is another thing. And we believe the efficiency of the spectrum and doing it as fast as possible to adapt to the traffic conditions are key. And therefore, we believe that our solution has a quite unique advantage to our customers we are looking forward to deploy throughout the year. So thank you very much.
Thank you very much for that presentation, Sibel. Now I would like to introduce Mr. Andreas Roessler from Rohde and Schwarz to share a test and measurement perspective on dynamic spectrum sharing.
Yeah, thank you, Sean, for the kind introduction. Thanks to Sibel for laying the foundation, for setting the bar on the topic. Happy to be here. I would like to take the remaining time to give you a little bit of a perspective on dynamic spectrum sharing from a test and measurement perspective. So first time we discussed dynamic spectrum sharing with RCR Wireless at Mobile Congress Americas back in October 2019. At that time we had a technical presentation on DSS and we showcased our test solution in terms of signal generation and analysis at the event with the intent to be used by infrastructure vendors to validate the implementation of DSS. So I've been asked what we did in parallel to that and what has happened. So I want to give you that type of information right now. So one of our most recent efforts, and I think Sibel mentioned that throughout the presentation already, was the validation of DSS with chipset vendors. And what we did in preparation for the Mobile Congress in Barcelona that was canceled, we worked closely with Taiwan-based chipset vendor MediaTek, and we executed different test campaigns to validate DSS functionality while using our new mobile radio tester platform for 5G in our device testing, the CMX500. In parallel, from a network perspective, we were working with a leading company that offers a UE simulator for lab-based 5G and our infrastructure testing to mutually validate the implementation of DSS on both ends. And of course, our plan was to demonstrate these collaboration efforts on modem testing as well as on the network testing side in 2 demonstrations at the now canceled Mobile Congress 2020 Barcelona due to the virus. So these 2 individual demos would have been the result of the recent months of testing with our partners and demonstrating the readiness of the CMX500 for testing dynamic spectrum sharing. For those of you who are more the visual guy, I put in here the link to the YouTube video and you will see my colleague Ricardo taking you through the demonstration, which is about a 2-minute video, so not that long to watch. In addition to these fundamentals, we worked with, for example, US-based tier 1 network operators that announced the rollout of DSS back in 2019. I think Sean touched on that at the introduction. We provided feedback to their DSS-related test plans, which the providers will use to validate DSS functionalities on devices before they are allowed on their 5G networks. So our team offered guidance on test case definition, supported the implementation of these test cases using the CMX500 tool chain, and then of course validating them with pre-commercial devices powered by the latest generation of 5G modems. So that is what happened on our end. The next step was a question about how DSS helps in the transition from the now deployed non-standalone mode to standalone mode. I think also Sibel mentioned that. Here you see a valid example where what we see in the industry right now happening, especially here in the United States, that operators can now also provide a coverage layer using 5G and R at the lower frequency bands, for instance, in the 800 megahertz range. So typically what happens is that an operator looks at his LTE spectrum portfolio and identifies the band that has the least impact on the LTE capacity, deploys, for instance, their standalone mode carrier, like shown here. But then, of course, you can see with a 5 megahertz bandwidth and 2x2 MIMO, even if NR is more spectrum efficient than LTE, you would run into capacity issues pretty quickly while you're transitioning your subscribers over to 5G NR. So what DSS does and helps with is, of course, if you now take the remaining LTE frequency bands that you are using, of course, dependent on the market, and enable DSS on them, then, of course, you can utilize carrier aggregation here in order to create the wider data pipes. And for simplicity, I basically do here not co-located sites so that we can have a clearer view on that what is happening. And you clearly see here on the right low corner what kind of data rates you could accomplish while the DSS is deployed and your scheduler is scheduling basically the entire LTE carrier for NR. So that's, of course, a theoretical value, but of course, it will help in the transition from NSA, from a pure NSA to a standalone mode, creating also the wider data pipe. If we want to stick to the question on the LTE capacity, I think that has been brought up a couple of times. I think Sibel had a few simulations that showed the advantages of DSS rather than a static sharing, where you're splitting a carrier. If you look at what is being taken away, definitely from LTE to enable DSS, is you need to roll out MBSFN subframes. The question is how many and what the periodicity is to enable 5G NR. So here you see basically the time representation of that. So I'm plotting here a full radio frame of 10 milliseconds on the x-axis, and then on the y-axis you see a periodicity of 4 radio frames. If you remember your MBSFN classes from LTE release 9, there could be up to 6 subframes out of 10 possible subframes being used for MBSFN. I call them here the MBSFN candidates, framed in blue. But then, as you can see, for DSS, only 3 out of a total of 40 available subframes are actually being configured for MBSFN, and they are required to carry the synchronization signal blocks that the 5G devices for initial access, but also track and reference signals for channel equalization in the receiver side. So the SSBs have a periodicity of 20 milliseconds. That's why you see them here twice. And the TRS actually need 2 consecutive subframes by 3GPP definition, but can run on a periodicity of, for example, 40 milliseconds. So 3 out of 40, that's how we got to the single-digit percentage by default. So that's taking away from LTE. That's about 7.5%. That's 7.5%. So not that dramatic impact at all. And then, of course, the remainder on the LTE capacity then depends on how your scheduling algorithm is balancing the resources between LTE and 5G NR, and that depends on a lot of parameters, including the cell load, including the quality of service by the devices requested in that cell, how many LTE devices you have, how many 5G NR devices you have. And that is, of course, the secret sauce of the infrastructure vendors. Scheduling algorithm in general are proprietary, so there's not a definite answer that you can give here. But of course, it will be balancing that demands, as already explained by Sibel, and now here proven by myself. Okay, so the last thing I want to touch on is that the testing of DSS is not only something that's need to be carried out in a lab-based environment and being done with interoperability tests between infrastructure vendors and chipset vendors. We also always highlight that once the job is done and the feature is active, also the system performance teams of the service providers, of the network operators that are in charge for network maintenance and network optimization using drive test tools will be impacted by this. Typically, you use passive scanners and receivers as a receiver for determine network coverage based on measurements. In LTE, you use the cell-specific reference signals for that, and we're measuring RSRP, RSRQ, and signal-to-noise ratio. On those, what you see here on the plot is basically the y-axis spans frequency, in this case 1 resource block, so 12 subcarriers, and on the x-axis we have time, and I'm showing 2 subframes here out of a full radio frame. And as you can see here highlighted is a 2x2 MIMO scenario in yellow and blue. I highlight the resource elements that carry a portion of the cell-specific reference signal sequence dependent on the antenna port being used. And like I said, it's a 2x2 MIMO scenario. So the UE or the scanner used for network optimization would of course look into those symbols where we have these resource elements present, measure RSRP on these resource elements, so strip of noise and interference and everything, and just measure power. And then within the symbol, you would measure RSSI and put that into a relation to conclude on RSRQ values. And then also you can measure signal interference to noise ratio. So if we now activate a DSS, then from the explanation, you know that we have an MBSFN subframe now that is occupied by a 5G new radio. The first 2 symbols in that subframes are still LTE. So that's why we still see here in the very first symbol of that second subframe, these resource elements there that carry cell-specific reference signal. But at the end, you will have, if you don't tell the UE or the scanner that MBSFN is active, that the UE and the scanner will still take LTE-based RSRP measurements and RSSI measurements in those symbols. And that, of course, would lead to a different interpretation of the actual terminology and coverage. So what you need to do basically is you need to have the possibility to exclude these MBSFN subframes from actual LTE coverage measurements. And the good thing is, or the good news is that this is already supported by Rohde and Schwarz mobile network testing solutions. You see here on the right-hand side, the TSMA-6, our autonomous scanner that can scan up to frequencies up to 6 gigahertz, all technologies in parallel. And on the left-hand side, you see a screenshot from the Rome's drive test software, the collection tool interfacing towards the scanner, and that has MBSFN implemented already. So we can just reuse those features and enable the network operator community to assess LTE coverage while DSS is still active. And the beauty, I think, to highlight here is also that the scanner has a smart scheduling algorithm inside and assigning scanning resources to different technologies, different frequency bands, so that can be easily used to scan LTE and NR in parallel. So with that, a little excursus on what DSS means from a test and measurement perspective. With that, I would like to hand it back to Sean for further discussions.
Hey, thanks very much, Andreas. You know, we've got a lot of questions here, and I don't think we're going to have time to get to all of them, but we're going to try, and we'll follow up individually as needed. But Sibel, a lot of the questions here, if I can lump them together maybe, are regarding the relationship between DSS and non-standalone networks and standalone networks. And then I think several of these questions kind of speak to the distinction between dual connect and dynamic spectrum sharing. So could you maybe draw a distinction between dual connect and DSS, and then talk a little bit about the applicability of DSS as it relates to non-standalone and standalone?
Sure. Maybe I can start kind of zooming into spectrum sharing question first, whether it's valid between NSA and SA. So, I mean, as a technology, I mean, this is a tool to be able to enable NR in 5G and LTE spectrum. So, and that spectrum will be visible as a 4G to the 4G device and as 5G to the 5G device. So everything that you build on top of it, like standalone, dual connectivity, everything else is just another layer which is independent from spectrum sharing. So if I just zoom into NSA and SA, So let's say that you have a certain FDD band and you would like to do spectrum sharing. And as you know today, all initial devices supporting NSA, and there will be a gap to supporting SA supporting devices. And therefore, all current existing deployments and launches in ESS is happening in NSA architecture, which means that you need an LTE anchor to be able to activate the NR band in that carrier. But ESS works both for NSA and SA. As I said, this is a completely independent discussion. And when operator migrates to SA, that band and ESS will work exactly the same way. It's just about the device support for SA, not for ESS, anything specifically. And that basically works for both architecture. And if I say a few words on dual connectivity, again, this is, LTNR dual connectivity is a mandatory thing to do to be able to run NSA. So you need an LTE anchor to be able to connect to 5G carrier. Well, if that carrier is 5G mid-band or high band or low band is regardless. So this is not a competing technology. It is just a complementing solution that is mandatory for NSA, and it can be, this is basically to be able to launch the 5G in any band. That is not really competing with ESS. And it is working both for SA and NSA for ESS.
Great, thank you very much. And, Andreas, I think you touched on this on your final slide, and it includes DSS, but goes beyond that. But when you look at the just variety of band combinations you get with 5G, just the general complexity, what does that mean for the automation of field test processes?
Yeah, good question. I think the easy way for us to answer that is that our scanning solution has a smart scheduling algorithm built in as well. So what that means for us is that we can scan from a technology perspective everything in parallel, and we can give to certain technologies priority and add more resources to that. So the beauty thing of that is that, for instance, we can focus on 5G and R and LTE, and even weigh on different bands to spend more resources and measurement time on them. So we are lucky in that regard that we can run all these testing based on one unit. So for us, in the combination of bands, how this is being rolled out, it really doesn't matter.
Thank you, Andreas. And Sibel, I'm going to again try to paraphrase and join together several questions here, but I think some of these are essentially asking, do you see DSS as a transitory technology? And if so, does it have sort of a limited time frame for entering the market? And then just to expand on that, you mentioned DSS as a potentially foundational technology to 6G. So maybe you can address the transitory question and then tell us a little bit more about what you see going forward long term.
Yes, of course. So as I try to highlight in this performance slide, we believe that DSS is not a transition technology because this is an innovative solution where you can increase the spectral efficiency regardless of the penetration of the devices. So even in a case where you have same amount of device in both technologies, dynamic spectrum sharing is always provides higher spectral efficiency and higher user throughput compared to static sharing, which means that we believe spectrum sharing will live very long, and not only for FDD bands or between 4G and 5G, but it will actually be used for all the bands between all the technologies. And that is the reason I mentioned, I believe personally, that this will be a technology will be definitely be discussed when we are discussing 6G.
All right, thank you very much. And then, Sibel, you could jump in on that and discuss a little bit more from the software perspective, what's happening automatically at the base station to allow for this interference to not happen.
Yes, so if I understand the question, Sean, so it's related to how dynamic spectrum sharing can help to reduce the interference. So is it the question?
Yes, I think, yes.
Yes. So it is simply due to pooling gain. So basically with spectrum sharing, what you do is instead of dividing a certain band for any technologies, which effectively means that you need to carry the same amount of traffic with lower amount of bandwidth, which increases the load and which load increases interference between cells. So by enabling a higher spectrum to different technologies, and the fact that when that spectrum is, and when 4G is for 5G or any technologies alone, and the fact that they can access to all spectrum in once, it will not only increase the amount of the spectrum that can be available to that device, it also means that you can actually adapt and balance the load. And when you balance the load, then you create less interference to your neighbor. So it basically have a double impact to the user throughput by using spectrum sharing, and effectively means that that is the main reason why you have 3 times increase on the user throughput to LTE user in this situation, because you simply both increase the amount of spectrum available and you're decreasing the load from your neighbors that is creating interference.
Great, thank you very much, Sibel. And then Andreas, we've got a question here that gets into the MBSFN subframes. You went over this a little bit in your presentation, but if you could maybe specifically address, is there any concern that some LTE legacy devices may not be able to handle MBSFN subframes properly?
Yeah, that's a good question. I think the very first thing that we did in terms of DSS testing, since Rohde and Schwarz was one of the few providers that supported MBSFN in their mobile radio tester platforms, is that we actually configured according to what seems to be the configuration for MBSFN in the network, our emulator, and then used commercial devices, LTE only commercial devices, to see if they would follow the broadcasted information, and they all did. So there was no real surprise there. So I think every of the chipset vendor did a good job to implement that. At the time, MBSFN was standardized and then implemented into the chipset. So it's actually one of the essential tests that network operators did in the very first case, without really testing DSS, more testing on the MBSFN side and testing LTE commercial devices for it.
Great, thank you very much, Andreas. And then I think we have time for one more question. Sibel, you covered this late in your presentation, but DSS is a sustainability mechanism. This is something that you explained to me, and it's pretty interesting. So maybe you could share a little more detail around that aspect of Ericsson spectrum sharing with our audience.
Definitely. Of course, when you get technology and that you basically come with a NIP spectrum and you invest in certain hardware, and of course you spend a lot of time to bring that solution to the hardware to the sites, and quite let's say long lead time and quite big impact to the operators to be able to make these launches. What is really important especially in the technologies that we are now creating a new technology every 10 years. Of course, we want to be able to use what we have deployed. And when we were starting for our new hardware a few years back, we already considered the fact that there will be, of course, 5G coming in 2020 or 2021 timeline, and the fact that we need to be prepared for the possible impact that can come from this new technology so that we are prepared. And this, I think, definitely paid off. And this is not only, as you said, a cost thing, and it's not only the time to market thing, it's definitely a sustainability thing. So with this solution, then our operators doesn't need to go to site, change the hardware, and put a new baseband or new radio to be able to run this new solution. This, as a result, will definitely have a big impact to our environment, because then we can actually sustainably use this new hardware for many years to come for 5G as well.
All right, well, we've reached the end of our session here. Sibel, Andreas, thank you very much for taking the time to join the discussion today. To the people that attended, thank you for your time and attention, and a reminder that we'll have a recording of this available as well as a companion report, so look out for that. Thank you.